We now start the presentation of module 3 of chapter 5, and the main topic of this module will be a convergence theorem. We go to the first slide. We start this last module of chapter 5 with a very important theorem which is known as bounded convergence theorem. Suppose f n belonging to n is a uniformly bounded sequence of Lebesgue integrable functions defined on a measurable set E of finite Lebesgue measure. By uniformly bounded, what we mean is that there is a common bound, positive real number capital M say, such that for all x belonging to E, mod f n x is less or equal to capital M, and this is true for all n belonging to capital N. And suppose that this sequence f n is pointwise convergent to f almost everywhere on the set E. Then the conclusion is that f is also Lebesgue integrable on E, and moreover integral of f over E can be obtained as the limiting value of the sequence of values of the integrals integral f n d mu. We start the proof. Since f n converges to f almost everywhere on E, so from the definition of almost everywhere, we can find a measurable set B subset of E whose Lebesgue measure is 0, such that f n converges to f everywhere on the set E minus B. Now, on this exceptional set B, where we do not know anything about the convergence, set the values of all the functions f n as well as the limit function f as 0. Then obviously see that on the whole set E, now f n converges to f. Observe that since on this exceptional set B, we have taken the values of all the functions 0, this in any case does not affect the values of the integrals of f or f n on the set E. Since the function sequence f n is uniformly bounded, suppose that mod f n x is less or equal to a positive real number capital M, and this is true for all x belonging to E. Then if we take the limit n tends to infinity on the left hand side, we have mod f x is also less or equal to capital M, and this is true for all x belonging to E. So, f is bounded. Since each f n is measurable and f n tends to f pointwise on E, we know that the pointwise limit of a sequence of measurable functions is also measurable. By that argument, f is also measurable on E. Hence, f is both bounded and measurable on the set E, which is of finite Lebesgue measure, and so f is Lebesgue integrable on E, and this proves our first assertion. For the second assertion, choose epsilon greater than 0. Recall the Egorov's theorem. Now, recall that in Egorov's theorem, what we had proved is that if f n is a sequence of measurable functions which converges to a measurable function f almost everywhere, then the sequence of measurable functions f n converges almost uniformly to the function f. What does that mean? This means that given delta greater than 0, we can find a measurable set B whose measure is less than delta, and outside the set B the convergence is uniform. So, if we apply Egorov's theorem to our sequence f n here, we can find a measurable subset A of the set E such that mu of A is less than epsilon by 4 m, this is our delta, and f n converges to f uniformly on the set E minus A. Subsequently, from the definition of uniform convergence, we can find a positive integer n such that mod f n x minus f x is less than epsilon by 2 mu e, and this is true for all n greater or equal to n as well as for all x belonging to the set E minus A. Now, for all n greater or equal to this particular positive integer capital N, we get mod integral over E f d mu minus integral over E f n d mu. This is less or equal to integral over E mod f n minus f d mu, and we can divide the set E into two disjoint parts A and E minus A. So, this is equal to integral of mod f n minus f over the set A plus integral of mod f n minus f over the set E minus A. The first integral is less than epsilon into mu A by 2 mu E, and the second integral is less than 2 m into mu E minus A, because we can use the uniform boundedness here. So, the whole product is, the sum is also less than epsilon, and this shows that integral of f over E is obtained as the limit of integral of f n over E. Why this theorem is important? Because if we consider the function f n defined on closed interval 0 1 in this way, that f n x takes the value 1 if x is equal to r 1 r 2 r n and 0 otherwise, where r n is the sequence of rational numbers in closed 0 1. Then see that each f n has at most finite number of discontinuities in closed interval 0 1, and so is Riemann integrable. Obviously, the sequence of functions f n is uniformly bounded by 1, but this sequence of functions f n actually converges to the function chi q pointwise on the whole interval 0 1, and we already know that this function chi q, which takes the value 1 for all rational numbers and 0 for all irrational numbers is not Riemann integrable. So, we have a sequence of functions which is uniformly bounded. Every function is Riemann integrable, but the limit function is not even Riemann integrable. So, the bounded convergence theorem gives us a result which shows that the process of Lebesgue integration is much more stronger than the process of Riemann integration. See, we already had one integration process for bounded functions which is Riemann integration, and we have defined a new integration process which is Lebesgue integration. We have already seen how this new integration process is more useful than Riemann integration, in the sense that some functions which were not Riemann integrable earlier, like function chi q, is now Lebesgue integrable, and we know the value of that integral. But what happens to those functions which were Riemann integrable? Now, whenever we extend a concept, we always want that the extended concept is such that the objects which had earlier property still have that property. So, in the view of that, we have this particular theorem that if a bounded function f is Riemann integrable on closed interval a b, then it is also Lebesgue integrable on closed interval a b, and moreover for these functions the values of the integrals with respect to Riemann or Lebesgue are same. We start the proof of the theorem. Let pi a b denote the set of all partitions of closed interval a b, and for any partition p of closed interval a b, as usual, let LPF and UPF be the Riemann lower and upper sums of f respectively. And we know that the lower Riemann integral of f over a b is equal to the supremum of all lower sums LPF, where p runs over pi a b, and the upper Riemann integral of f over a b is equal to the infimum of UPF, where p runs over pi a b. Now, again from the observation that supremum or infimum of a set are limit points of those sets, and we can find sequences in those sets which are convergent to those limit points. We can choose sequences of partitions Pk, k belonging to n, and a sequence of partitions Pk dash k belonging to n of closed interval a b, for which the lower integral of f over a to b is obtained as the limit of the sequence L Pk f, and the upper Riemann integral of f over a b is obtained as the limit of the upper sum U Pk dash f, where limit k tends to infinity. Now, take the first two partitions P 1 and P 1 dash and take the refinement theta 1. So, we take theta 1 as P 1 union P 1 dash. Take theta 2 as P 1 union P 1 dash union P 2 dash union P 2 dash. So, obviously, theta 2 is a partition which contains theta 1. Define theta 3 as the union of P 1, P 2, P 3 and P 1 dash, P 2 dash, P 3 dash and so on. Then this sequence of partitions theta 1, theta 2, theta 3, this is a sequence of partitions of closed interval a b which is monotonically increasing in the sense that theta 1 is subset of theta 2, this is subset of theta 3 etc. And since we know that for a refinement of a partition, the upper sum decreases and the lower sum increases. So, if we apply the sandwich theorem of real analysis, we get lower integral of f over a b is equal to limit over k L theta k f, and the upper integral of f over a b is limit over k u theta k f. Now, consider a typical partition, say theta k. Suppose theta k is given by a is equal to x 0 less than x 1 less than dot 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 less than x n minus 1 less than x n equal to b. Let small m I is the infimum of f x where x runs in the interval x I minus 1 to x I, and capital M I is the supremum of f x where x runs in the interval x I minus 1 to x I, and this is true for all I is equal to 1 to n. Define a function L k x in this way. L k x takes the value small m I if x I minus 1 less or equal to x less than x I for I is equal to 1 to n, and at the point x is equal to b it takes the value small m n. And consider a function u k x which is defined in this way, that u k x is equal to capital M I when x I minus 1 less or equal to x less than x I for I is equal to 1 to n, at x is equal to b it takes the value capital M n. From the definition it is obvious that both L k and u k are simple functions, and all the functions L k are less or equal to the functions u k. So, we have two sequences of simple functions L k and u k such that Lebesgue integral of L k x over a to b is equal to L theta k f, and Lebesgue integral of u k x from a to b is equal to u theta k f. And these two sequences of functions L k and u k are related to the function f in this way, that L 1 less or equal to L 2 less or equal to dot dot dot, and all the functions are less or equal to the function f, whereas u 1 is greater or equal to u 2, this is greater or equal to u 3, and this is greater or equal to dot dot dot, all the functions are greater or equal to f. So, the sequence of functions L k is bounded above by the function f, whereas the sequence of functions u k is bounded below by the function f. Since both the sequences of functions are monotonic, and since f is bounded. So, all these functions are bounded and actually they are uniformly bounded. So, it follows that limit k L k and limit k U k, both the functions exist. Define L x as the limit function of L k x and define U x as the limit k U k x for all x belonging to closed interval a b. So, L is the limit function of the sequence L k and U is the limit function of the sequence U k. Then being the pointwise limit of sequences of measurable functions, both L and U will be measurable, and also L is less or equal to f and less or equal to U. And from this relation, it now follows that since integral over U and integral over L are equal, so integral over a to b of the function u minus L will be 0 and u will be equal to L almost everywhere, and consequently u will be equal to f equal to L almost everywhere, and this will show that f is also measurable and so is Lebesgue integrable, and the values of both the integrals are equal. So, we have seen that if f is a bounded function defined on closed interval a b, and if f is Riemann integrable on closed interval a b, then f is also Lebesgue integrable on closed interval a b. But we have also come across improper Riemann integrals, that is the functions which are Riemann integrable in the improper sense on infinite intervals. For example, if we consider the function f x is equal to sin x by x when x is not equal to 0 and equal to 0 at the point x is equal to 0, we know that the value of the improper Riemann integral 0 to infinity sin x by x dx, this is pi by 2. So, this function is Riemann integrable in the improper sense, but this function is not finitely Lebesgue integrable, because we can show that mod sin x by x, if we integrate it from 0 to infinity, then the value of the Lebesgue integral will be infinity, which is given in the course content. So, summarizing, in this module, the last module of chapter 5, we have seen that a very important convergence theorem, namely bounded convergence theorem, holds for Lebesgue integration, and also we have seen that the functions which were Riemann integrable, bounded functions on closed interval a b, they become Lebesgue integrable on closed interval a b without affecting the value of the integral. And we stop this module as well as the chapter 5 here.